Hey everybody, this is Mr. Tegmeyer again, and this is part 2 of the Introduction to Thermodynamics presentation. And in this part we're going to cover convection and conduction. So let's look at the different kinds of thermal energy or heat transfer. There's three basic kinds that we're going to look at: convection, conduction, and radiation. Radiation we're going to cover in part 3. And there's a couple of things that are very, very important. I've mentioned these before, and anytime you have to do anything related to energy, it's important to understand. You've heard me say it 1,000 times, and I think you know it already. 100% efficiency is unattainable. You cannot do it. The other thing with respect to heat is that all the processes that we talk about, all examples, are irreversible. So think back to the first presentation where there was an example of wood when we looked at the second law of thermodynamics. When you burn wood, it turns to ash. It's irreversible because you cannot take that ash and turn it back into wood and burn it again. You just can't do it. That's irreversible. So what is convection then? Convection has to do with the movement of heat through a movement of fluid. And a fluid, again, can be a liquid or a gas. So it could be air, could be water, it could be argon gas, it could be anything as long as it's a fluid. If you bake a lot, you might have a convection oven. Convection ovens use the air circulating through the oven to cook your food. Typically it will cook more evenly, it will cook quicker than an oven that uses radiation. Here they use an example of a boiler system, heating water and using that to heat your home. Oddly enough, not only does this system use convection, but it also uses radiation to heat your house. Well, conduction, on the other hand, has to do with two objects that are touching, or it could just be a single object where heat moves from one end to another or one side to another. And here you see a metal spoon that's put in, we're assuming it's a hot bowl of soup. So if you think of the tip of the spoon that's in the soup, obviously if you pull that out, that end is going to be hotter than the end where you place your hand. But what happens is if you leave the spoon in there, the heat is going to move from the tip of the spoon all the way to the handle. And when it reaches equilibrium, it's all going to be the same temperature. That is conduction. Well, now let's take a look at some equations and solve some problems. So one of the most basic, and you will see this a lot when you get to college, the basic energy transfer equation is Q equals mc delta T. Some people shorten that up and say Q equals mcat. Now let's take a look at those. So Q is just the heat or the energy transfer, and as a form of energy we measure that in joules. M is the mass in kilograms. C is a constant for every different kind of material, and it's called the specific heat. So if we have glass, for example, we would call it the specific heat of glass. If you have a plastic, each kind of plastic, is going to have its own value. Water has its own value, and so on. Excuse me. And then delta T, the triangle there is delta, that means change in, and T, of course, is temperature. And one thing that's important to know about any delta, whether it's delta T, delta M, as in mass or whatever, you always measure the final minus the initial to get the change in. So that's one important equation. Let's look at a couple more. So here we have three equations, and really there are actually two, and one is just rearranged. So let's look at the first one. P equals Q over delta little t. And in this case, P is the rate of energy transfer. We also know that in terms of electricity, we call that power. As such, we measure that in watts. Q, just like before, is the energy transfer or heat in joules, and then delta T, in this case, little t, and that's just a change in time, and we always measure that in seconds. So if we look at the second equation, P is the same. It's also equal to the thermal conductivity, which is also a constant for a given material. A is just the area that two materials are coming in contact. L is the thickness of the material, not the length. And we already have enough T's, so we call that L instead. And then delta T, of course, is the difference in temperature. Now you can rearrange that middle equation to solve for K if you'd like, and sometimes we would do that. So now let's look at an example. All right, so here we have a block of aluminum and we put it in some water. So let's read our problem and apply our process, our problem solving process, and let's solve this thing. So it says calculate the energy transferred when a block of aluminum at 80 degrees C is placed in 1 liter of water at 25 degrees. And we're assuming that it comes to equilibrium at 30 degrees Celsius. In other words, both the metal block and the water come to a final temperature of 30 degrees Celsius. The other thing that's important to know here is that 1 liter of water is equal to 1 kilogram of water. So our first step is to list all of our known values. So we know the mass of water, 1 kilogram. We can look up the specific heat of water. That's something that I would give you or the problem would give you. In this case, it's 4184. The units are joules per kilogram degrees Celsius. That's how we say that. We know our change in temperature for the water is 30 degrees, which is our final, minus 25. That's 5 degrees. And we know our specific heat of aluminum, because we can look that up, or that would be given to us. That's 900 joules per kilogram degrees Celsius. And the change in temperature of the aluminum is 50 degrees. Now, technically, it would be minus 50 degrees. But in this case, we're considering just the absolute values. Now let's list all of our unknowns. Well, we don't know what the energy transfer is, and we don't know what the mass of the aluminum block is. So what are those relationships or the equations that we know? Well, we know Q equals mc delta T, and we also know, this is important, that the heat given up by the metal block is equal to the heat absorbed by the water. Those two have to be equal for us to come to thermal equilibrium at 30 degrees. So let's solve for the Q of the water, the heat of the water, how much that absorbed, because we know the mass of the water, we know C, and we know delta T. So when we plug and chug, we get that the water gained 21,000 joules. So now let's go back and let's remember that the heat lost by the aluminum is equal to the heat gained by the water. Technically, that's 20,920 joules. So if we use our Q equals mc delta T for aluminum, and we rearrange and solve for M, and plug in our values, 20,920 joules divided by the specific heat and temperature change, we get a mass of 0.46 kilograms or 460 grams. Pretty easy. Let's do another one. Here we have a section of wall, and it says, let's just go ahead and read it. Calculate the energy transfer in a wall section, and it gives us the area 2 meters by 1 meter, and it says it's 0.04 meters thick, or 4 centimeters. It has a thermal conductivity of 0.1 joules per second meter degrees Celsius. Those are the units. And it tells us that the opposite sides of the wall have temperatures of 10 degrees and 5 degrees after 1 hour. So it gives us temperature difference, and it gives us some time. So let's list all of our knowns. We know the area, it's just 2 times 1, so it's 2 square meters. Our thermal conductivity is given to us up above. It's 0.10. And note that the units are joules per second meter degrees Celsius. Always remember your units. This is why this type of problem, knowing the units is so important. Because if you write the wrong units, you can easily come up with the wrong answer. And using units as a check on the end, you can go back, and that's a way to check and see if you've done it correctly. Well, our L is not our length. Remember, L is thickness. We know our change in temperature, our temperature differential, and that's 5 degrees. And 1 hour equals 3,600 seconds. So what are we trying to find? Well, we need to find the rate of energy transfer, or power, and just the energy transfer itself. So these are the equations that we are going to use. So you can see the first equation, we don't know P and we don't know Q. That's a problem. So we need another equation. Well, we know another equation for P, and that is K times the area times delta T over the thickness. So if we substitute Q equals P, and then P times delta time, and then we combine those, we can write the equation like this. Q equals the quantity K times A times delta temperature over the thickness times delta time. So let's plug all those numbers in. We plug those numbers in, we get 90,000 joules, and that's what we're looking for.